Okay, Physics 20. So we continue on with this practice here. Hopefully we can do the rest of it here from 44 to 74. All right, so an astronaut is in a space shuttle orbiting the Earth, performs a trick for a television audience, blah, blah, blah. Got to zoom up. I can't move upwards here. Okay. She inflates a helium balloon filled with within the space shuttle, no air environment, and let's go. Well, it rises away from her, it falls, drifts back in the opposite direction of the shuttle's velocity. No, it'll probably just hover in place where it's released. If there's no air, so there's nothing to push on it, she releases it. It's still going to be affected by gravity. She's releasing it at the speed at which the space shuttle was going. It's orbiting, so I'm assuming it's just going to hover there when it's released. Relative to that, like, it's going to move around in a circle with the space shuttle. It'd be weird if it didn't. Oh, let me just get my pen in the right one here. So I think that's going to be A. Okay. There's really not much else to do that one. Seems it would violate physics if it did anything else. So, and I wouldn't raise away from the Earth, because the reason a helium balloon raises upwards is because there's air and it's less dense than the air, and there's a buoyancy force pushing up on it. That's more than the atmospheric pressure pushing down on it. Yeah, so if there's no buoyancy force, so it would just stay where it's released. Yeah, if it's in absence of air. Okay. If there was air, it'd probably move up. Would it? No. Moving in a circle. Yeah, it'd probably go upwards, but since there's no air, there's no buoyancy force. Strange. Okay, I say just hover in place. When a force of 18 newtons is applied to an object, the work done is going to be 400. Oh, so we're in the energy, 454 joules. What distance does the object move? Oh. I don't know. Oh, it's just going to be force times distance. Okay. I was thinking, is it moving upwards? Is it changing its velocity? Like, but if we go force times distance, right? F is equal to force. Or sorry, force times distance is equal to work. Poop on that. Okay. Then this should be a pretty easy question. I don't know why I was thinking so hard about this question. Work is equal to force times distance. We're looking for D. That's going to be work divided by force. So that's going to just be joules and newtons. So those are good units. 25.2. That's going to disappear. There you go. Okay. Oh, yeah, it did disappear. All right, so a stationary 25 kilogram object is released from a point quite far away from the Earth. Okay. Stationary relative to what? Relative to the, yeah, okay. I'm going to ignore that fact. At what speed just before it impacts the ground? Just before impact. I'm trying to figure out what they're trying to do here. So that distance is going to be quite far up. Since that distance is so far up, acceleration is not going to be 9.81 anymore. This is a weird question. But what if we assume the acceleration to be 9.81 at that distance? And then it's going to accelerate as it gets closer. And the Earth is doing work and it's adding energy to the system. Well, this is an interesting question. I don't know how they expected this to answer this question. Let's just say, relative to what? Relative to the ground? what's my E? So maybe I want to find the distance relative to the ground here. I just want to know the distance it has to cover. I'm just going to find this out first. Okay, so you're going through the thought process of me, because I've never done this question before. This is a weird question. Let's do 6. I'm going to minus away the radius of the Earth. 6.37 times 10 to the 6 as well. So it still has to drop a significant distance. So 2,530,000 meters to drop down. Okay, so I just want to quickly do something in my head here just to see if this is what they expected to happen. And then I'm going to just times that by 2, divide by the mass, take the square root. Yes, that's 7,000. This could be an answer. I don't know if I like that answer. Because gravity is not 9.8 up at that direction. Because you have to assume that when you do this equation, like this is what I'm doing right now. So I did this. Like the potential energy way up there is going to be equal to potential kinetic energy way at the ground, because, well, if I go through the steps of what I'm doing here, if gravity is the only thing acting on the system, then it's isolated. But the problem is here is that the distance is so much further out that gravity's acceleration is different than where it's on the Earth. We make the assumption that the force doesn't change. All right, that's why we can say it's a conservative force. But here, the force is always changing. It's getting bigger and bigger and bigger and bigger and bigger as we go down. So that's always changing. So actually, the Earth is actually doing a considerable amount of work. So what is that going to be? What are we going to do here? Like I got 7,000. I don't know if that is that the answer they want. I'm just going to double check my answer key, or their answer key. You're getting my mumbling. You probably skip past a bunch of this here. I'm just going to go to my answer keys over here. This is my review. What do they want here for an answer? It's going to load up on the screen here. So this is question what? This is question 46. So what do they say? Well, they went with A. Okay, that makes more sense. But again, I think they're taking the fact that it's ever changing. Let me just think about this question. Okay, so this must be a hard. What I'm going to do is I'm going to create a graph, because the area of a force distance graph is going to be the work done. All right, so if I can find the work done, which is the change of energy, and the energy that's changing here is going to be my kinetic energy, and then I can use that because it's released. So I'm going to say my VI is equal to 0, and my EKI is going to be 0. All right, so yeah, let's just see what the force here. So I'm going to create a little force times distance graph here. Okay. So here's my distance. I'm starting from 0, going all the way up to 2,530,000. There you go, meters. And then I'm going to be going from a force to another force. So the force is not going to be a nice constant change here. This is going to be a really hard question, I'm thinking. So at the ground level, it's a pretty easy force. 25 times 9.81. So at the ground level, at the end of this flight here, its force is going to be at 245.25 newtons. So that's the force at ground due to gravity, right? So this is Fg. Okay. And then at the 0 point, so that's way up there at the 2 million mark, I had to find out what that force of gravity is by using at the very top here, because we have two forces of gravity. You got force of gravity, mass times gravity, or GMM over R squared. Mass times gravity is really easy. So this is at the ground. That's 9.81. That's where this number comes from. So here I'm going to calculate what the force of gravity is way up in the sky. 25 times the mass of the Earth 25, 24, yeah, 24, divided by the radius. They give us the radius, that's nice. I just use that, squared. So at the top, it's not 0 because it's still within the gravitational field here. It's at 125 point, I don't know, 67 or so. 83 newtons. Okay. So now as you move closer, that force is going to change, right? It's not going to change in a nice straight line. Still, this is a confusing question. Okay. So if I were to kind of draw a force graph here, and assuming that this would move in a straight line, but it's not, right? This is what the graph would look like. Okay. I'm going to get an approximate answer, right? I'm not going to get an exactness because this is going to be curved, right? It's going to kind of, yeah, it's going to be curved here. It's so strange because it's going to go like, it's going to be an exponential graph. But let's approximate it as this trapezoid graph here. So now we can find the area in this graph. So what's the change here? So I can do that. So the area of a force distance graph, force times time, is going to be, or sorry, force times distance is going to be work. So once I find this area is equal to work, which is equal to the change of energy. And by talking about this change of potential, because that's what I'm calculating here, change of potential, that's also going to be equal to the change of kinetic, right? Since the change of potential is equal to the change of kinetic in an isolated system. We're ignoring resistance. Okay? So let's just find out what this is. So this is a lot of button pressing my calculator, so I got to make sure I do that. So the height here, from here to here, is 119. Like you could split this into two shapes here. You can do lots of different things, right? And then you can make this into a triangle and a rectangle and then add them together. Or if you know your trapezoid formula, we can just use the trapezoid formula times the height divided by 2. So the change of energy here is going to be 469,224. Oh, that's not right. Millions, sorry, 299 joules or so. Okay, so now we know the change of energy. Since my EKI is equal to 0, this is equal to final minus initial. But my initial cancels out here, so that's just equal to final. That's my final. And I can find my final speed by rearranging the EK formula. So times this by 2. Times by 2. Divided by my mass. Take the square root. 6,126. So it's going to be that one. Yeah. I don't know how else they would have expected us to answer that question. That's a hard question. It almost requires integrals because it's a curved graph. It's going to be less than that, yeah, because it's curved. The area under that graph is going to be less than what we actually got. So that's a difficult question. Yeah. Yeah, I'm trying to figure out how else did we just solve this question. Because you can't use the acceleration's changing. It's like a jerking motion to it. Because it starts off at like 5 meters per second squared, and then it speeds up to like 9.81 meters per second squared. But again, that's a curved graph. I'm going to just go with the 6,000 because that's what the answer is. So it ends up being 6,127 if it's in a smooth line, but it's going to be less than that. maybe I have to use an integral between the two. Because that's what the formula is. Yeah, that's weird. Okay, never mind. I'm going to ignore that. That's what the answer ends up being. That's all right. This question, this practice is pretty hard. There's some questions here we don't have to worry about, like 46, and there's a couple of questions back there with bearing methods and stuff. Anyway, an object is resting on a horizontal frictionless surface. Attached, one end is a spring, then a spring constant of, that's a pretty big spring constant, 9,240 newtons per meter. The mass is pulled to a position of 4.75 centimeters and released. If the magnitude of the acceleration is that, what is the mass of the object? Okay, so let's see. So there's a lot going on here, but if it's a spring, we make the assumption that it's going to obey Hooke's law. Hooke's law says that the force is equal to negative kx. I'm not too concerned about the negative part. And this force, if it's on a nice horizontal surface, it's like the spring force, the restoring force, whatever you want to call it. If it's on a horizontal surface, frictionless, then the gravity force and the normal force cancel each other out, and the only force I have is this Fs. All right, so that's my net force. So my net force is this Fs, which is then equal to kx, right? Remember, net is also equal to mass times acceleration. So now I can rearrange this equation to find mass. So mass is equal to k times x divided by acceleration, which they give us. So our k is in newtons per meter. So that means I'm going to have to change my centimeters there to meters. So this is going to be important here. My acceleration is in meters per second, right? I think that's right. Let's see. Yep, meter per second squared. So, and then we put all the numbers in, and we should get our mass. So 9,240 times 0.07475, sorry, divided by 27. 16.25. Did I mess up somewhere? 9,200 times. Oh, there we go. So it's 14.9. I must have divided by the wrong number there. It's a good thing we have multiple choice here. 15.96 kilograms, which is rounds to 16. So that would be 16.0 if you were to round it properly. So there we go. Cool. Okay. In the diagram, two identical planks, A and B at different angles, used to slide concrete blocks from a truck. Comparing the amount of work done against friction by sliding the block down plank A and the work done against friction plank B. Pretty much D here. It'd be impossible to know unless we know the coefficient of frictions. Because I don't know if these planks are identical. Oh, the two identical wooden planks. Never mind then. All right. So these are identical. So the coefficient of frictions would be the same. Right? So so we should be able to figure this out. Work done. So we just have to figure out what the friction is. Right? They're both going to move the same distance. They're both identical. One's going to go at a steeper angle, but the length is going to be the same. So force times distance. That's the work, right? Work is equal to force times distance. In this case, we're talking about the work of friction. So the one that at steeper angle. So let's figure this out. So if we're at a steep angle, let me just draw a picture here. I'm going to draw a picture. I'll just draw one up here. This is just arbitrary. So we've got gravity going down. We have friction. We've got the normal force here. We got friction. So I got to find out what the friction force for both of these are. So the friction force is related to the normal force. Remember, force of friction is equal to mu Fn. So if the Fn goes down, the Ff also goes down too, right? So that's going to be related to our force of gravity here, our y component, and our x component. These meet at 90 degrees there. So if I can find out the y component, so the y component, so to figure out the y component, that is going to be the cos of the angle that they give us, right? So FGY is equal to whatever FG happens to be, doesn't really matter, cos the theta, right? So at the 45 degrees, this is going to be cos 45, so 0.707 times whatever, right? So let's just write this down, 0.707. And then at the 30 degrees, it's going to be 0.8 something, right? FG is going to be, remember cos 30 is 0.866, yeah. Okay, so the one that has the least amount of friction is going to be this one, the 45. So, which is A again. So this is the 45 is the A one, right? And this is the B one. Least friction, FF. So what are we trying to do? Comparing the amount of work done by the friction by the work against that compared to the amount. So B is more, right? Most friction, more FF, right? So it has more FF, then this would mean to have more work. There you go. These are hard questions. Kinetic energy, oh, this is a good question. I like this one. What happens to the kinetic energy of an object is increased the most by doubling its what? Its density. What's that garbage? Let's get rid of that. Its volume. Jeez. Doubling speed, right? So remember in the formula, EK is equal to 1/2 mv squared. So if I double V, I quadruple the energy. But if I only double mass, because mass is not squared, I only double my energy. So if I double my speed, I get quadruple. I get 4 EK. If I over here, I only get 2 EK. Okay. A car is a mass of this. If the, what will it be the speed? What? That's a weird question. It seems too easy. We had 2 really difficult questions up there, but then all of a sudden we had this nice easy question. Strange. That other question is really bugging me. I'm going to really think about that question over the night here. So I get about 17.98. Let me just write that down. Meters per second, but remember I want to change it to kilometers per hour here. So I get 64.76 kilometers per hour, which is going to be A. Don't have to change in these units, no. That's a simple question. All right, so on a frictionless cart is rolling along a horizontal surface, a force west acts on the cart, and it displaces 12 meters west. Okay, if the final speed is this, what is its initial kinetic energy? Well, it's a lot of moving pieces here, right? So there's a couple ways to do it. You can do the kinemax way and find the acceleration, then use that, blah, blah, blah. We're not going to do that. So what we're going to do, we've got force times distance. Right? That force is not changing its potential. It's only changing its kinetic. Right? So I'm going to use that information to help me find out what the initial kinetic is. Because remember, work, which is force times distance, is the same as change of energy, which is equal to final minus initial. And then I could just rearrange this for initial. All right. So let me see. If I want to rearrange this for initial, I would add over EI. So I can have the EI on this side. So I have my final minus my FD. All right, so I'm doing like a little swap here. I want my EI to be positive, okay? So to find my final, it's gonna be 1/2 mv squared, final speed, times my force and my distance, which we have. And I can find my initial. Because we're talking about kinetic here. On a horizontal surface, the change in potential is equal to 0, because I'm horizontal, right? So all this force is going into the kinetic energy. So force, is that 5.2? Yeah, 5.2 newtons times 12. So I get 64 newtons there, 62.4 newtons. 1/2 times the mass times the speed squared. This is for my final velocity here. So I ended up with 101.25 newtons, but from the beginning to the end, so I added 62.4 newtons, and I end up with 100 and some newtons. So that means I've got to start off with 38.85 joules of energy. What? I'm not doing newtons here. I got to fix all that. Can I do this? I know there's a button on here for eraser. Oh, that kind of worked. Come on, there we go. These are all in joules here. Cool. So that rounds up to 38.9. Okay, so in the diagram, we got a kitten jumping from a top of a 1.8 meter refrigerator to a 0.9 high counter compared to the kitten's gravitational potential energy on the top. Oh, it's half the distance. It's half as great. Yeah. Because it's half the distance. Yeah, that's weird. Well, I could just do this. Like, oh, here's my EP is MGH. And then over here, my relative to what? Relative to the ground? Oh, it could be infinitely times large. I don't know. Because they don't tell us where it's relative to. Well, I guess they're measuring to the ground if we say that. If we say it's relative to the ground. And then this is going to be like here. My mass doesn't change. Gravity doesn't change. I have half the height. So I have half of what I had before, right? So I have. Half is great. Yes. Some of these questions are really tricky. Some of the questions are misleading. I don't know. Snowboarder with a mass arrives at the bottom of a hill, glides across a horizontal stretch of ground, which is 38.5 meters from the bottom of the hill. Friction exerts a force, so that it arrives at the lift line at a speed of what? The speed of that. What's the kinetic energy that's at the bottom of the hill? From the bottom of the hill. Oh, so that's the horizontal distance. Okay. That really confused me. Okay. So we have this distance. We got a force of friction that's slowing us down. So this work here, which is this force times distance, will end up being a negative amount. So you have to kind of watch out. Remember these kind of questions. Is the force taking energy away, or is it adding energy to the system, right? So in this case, force times distance, you look at the formula sheet, which you can't see unless you cover my face up here. the formula sheet, there's a bunch of these absolute values on that formula. So when I go force times distance, and I get 3,657.5 joules, this is negative, right? Because the friction is removing the energy away from the system. But then it just stays, it's like a question of like two back. Where's that energy? If I'm on a horizontal road, horizontal surface here, my EP, change in EP is 0. So this change of energy that we have here is going to be just the change of kinetic, right? That's my change of energy. So this must be just my kinetic energy. So I've lost this much kinetic energy here, which is equal to final minus initial. Rearranging this again. So maybe I don't know what I'm going to swap here. So I'll swap those two there. So I got my EI to be EF plus 3657.5 joules. And my EK is going to be 1/2 mv squared again. So I'm going to do this again. It's going to be 1/2 mvf squared plus this work that we just did. So that kind of means that we started off with more work than we ended up with, which makes sense because I lost that energy. Times the speed, 6 squared. So at the end, I had 100.352 joules of energy because I lost a lot of energy. So I must have started off with a lot more. So let's just add on this number. I get 3,757.8 joules of energy, which is B. So be very careful. One's adding energy. This is like, I'm going to put it right here. Removing energy. All right, I'm going to go up here. This one's adding energy. So this is a positive number here, right? So a cart with a mass of 1.25 kilograms is rolling down an inclined plane at a speed of this. At the instant, it is 2.5 meters from the end of the incline. The incline is tilted at this. What is the mechanical energy of the cart relative to the base of the plane? Oh, okay, so we got to draw a little picture. We got to do some math, trigonometry here. Hi there. So at this point, we have a V of 1.7. So remember, mechanical energy is the sum of all the energy. So all the EK plus all the EP, right? So to find the kinetic energy, I'm going to go 1/2 mv squared. And this one here, I'm going to go mgh. It says relative to the base of the thing. So we have to know the height. So what is the height above this point here? So I know this distance is, what does it say? Actually, it tells you what it is. 2.5 meters. But that's not the height, so I can't use that number to do this question. So if I know the angle is 52 degrees, I can use trigonometry to find this height here. So we're going to use sine. H doesn't stand for hypotenuse, right? So you kind of watch out by labeling here. So I'm trying to solve for the H. I know the hypotenuse is 2.5 meters. So the height of this triangle is sine 52 times that 2.5. So 1.97 meters above the ground. Bunch of zeros there. Okay, so then I can go back over here and I just type all this in. So 1.25 times 1.76 meters per second squared. So we have 1.936 joules of kinetic energy. And assuming we're on Earth here, we have approximately 24 joules of potential energy, and we're going to add these together. Get 26.1. So I actually get 26.093 joules, which rounds to A there. Okay, if a machine is improved so that it exerts twice the force through 3 times the distance in 1/2 of the time, then this new power rating is, oh man, power. So what is power? Power is work divided by time, force times distance divided by time, and now I'm just going to go through and put all this stuff in here. So we have, because they're twice the force, 3 times the distance at half the time? Half of the time. So that's what I'm going to do. I'm going to take all these numbers now. So I got 6 on the top. I got a half on the bottom. Combine the 6 and a half together, you get 12. And that's my new number. So I got 12 here. So it's 12 times the rate. Is that what they said, 55? Yeah, cool. Okay. As shown in the diagram, a student exerts an average force of 600 newtons to lift the crate 3 meters. Compared to the work done by the student, the gravitational energy gained, it's the same. Oh, maybe not, because of, it doesn't say that it stops, does it? Yeah, okay, so the student's going to do 600, so the work of the student is going to be 600 newtons times, because it's going to be force times distance. It's going to be times 3 meters. So to figure that out is 1800 joules. Okay, so the student added in 1800 joules of energy. To figure out the change in potential energy, which is this final minus initial, we'll assume the initial is 0. I'm just going to go mgh. Okay, let's say 0 is the ground, or wherever it starts. So this is going to be 50 times 9.81 times 3. Oh, just a second. How's that possible? 50 kilogram times 9.81 times 3. That's 1,000. Oh yeah, never mind. 1,471.5 joules. Now you got to think, okay, where did the rest of this energy go? He added 1,800, but he only gained 1,400. So the rest must have went into the kinetic or lost due to friction or something. It's got to go somewhere. So in this case, it's not exactly the same, right? It'd be nice if it was. It's about 330. What, compared to the work done, the gravitational is less. Yeah, 330 less. It makes sense. It would have to be less. It'd be weird if it's more, because how would that work? Yeah. Okay. A dam is used to block the passage of a river to generate electricity. Approximately blah, blah, blah falls each second through each second. So that means probably time is going to be 1 second. At height, if 1/2 of the gravitational potential energy were converted to electrical, how much power would be generated? So we got to find the EP here, or technically the change of the EP. So we've got the mass, we got G, we got a height. Oh, that's not bad. Okay, so, and we got time. So remember, power is going to be equal to, oh, that's a horrible looking P. Power is equal to work divided by time. Okay, so work is our change in my energy. But we're talking about gravitational potential energy, so we're going to take that and divide by 1 eventually. So we're going to find the EP over here. So 57,500 times 9.81 times 19.6. So the EP is 11,000. That's not 11,414.8 joules. Only half of that is actually used. So I got to times this by half. Right? It says there half of it. Right? So divide by 2. So 5.5. So it's going to be A, because you're going to divide this by 1. Dividing by 1 doesn't do anything. It's actually 5.51 if I use the proper sig digs, unless I made a mistake here, but 1, 2, 3, 4, 5, 6, yeah. Joules, and then I go over here and divide it by 1. So 5.51 times 10 to the 6 watts. We have to go through and change all these answers or make appropriate answers. Get rid of some of the questions too that we don't need to worry about. Okay. Yeah, cool. Okay, in the diagram shown, the spring is compressed at 21 centimeters. At this position, the mass is 1.5 meters above the ground. The mass is released and shoots up. And as a kinetic energy or elastic constant, accelerates the mass up the frictionless plane. It coasts up, losing speed as it moves. How high will it be when it has this speed? Okay, so it's all about so that's its rest position. Okay, so when it's compressed, it's all going to be an EP. So maybe that's what we want to find out. What's the EP? So Hooke's law says, or actually Hooke's law, we find the EP going 1/2 kx squared. So I want to do this first. So I got 1/2, I got the K, 5,600 newtons per meter. So that means I'm going to want to change the compression of that 21 centimeters to 0.21 meters. I'm going to make sure that's squared. Okay, so this is my elastic potential energy. Let's see. So here I have 123.48 joules of potential energy at this point. Okay. Hi. So where does this potential energy go? Well, it's got to go into either one of two things. It's going to go into kinetic originally. It's going to be converted to kinetic and potential because it's pushing it upwards as well. And then as it goes, it's going to lose its kinetic a little bit and become more potential. So this is like my initial energy. It's how much energy I start off with. It could be like my mechanical energy. Let's imagine that. So this becomes mechanical energy. It's my initial. So my final mechanical energy should be this same amount. If my system is isolated, I think it says somewhere in the question, it's frictionless surface, and that's going to be equal to EP plus EK. So I can find the EP here by minusing over that EK. Okay, so actually let's find out what the EK is first. So at this height, it's 3.75 meters above the ground. The box is, how heavy is the box? 7.2. So I'm going to be using 1/2 mv squared to find out what my EK is. 1/2 times 3.75 squared times the 7.2 mass, kilograms of mass. Yep. Kind of do that out of order. As long as you square the right number, you're fine. Okay, so I have 50.6 joules of kinetic energy. I should have 123 joules of energy altogether. So what's left over must be in my gravitational potential. So I'm going to minus that over to the other side there. 123.48 minus this answer we just got. So my EP must be 72.855. Remember, that's equal to mgh. I'm trying to find H2 here. So I'm going to divide by, take this EP and divide by M and G. Then give me H2. I don't know what that will be. Let's see. Divide by M. And How did I mess up? How high above the ground is that? I only got like 1 meter. Oh, this is at the max compression. I forgot to add that piece in there. So, okay. So this is EP, but I also have to add in the other EP. Let me just go through and fix that. So over here, I got 2 forms of EP. I got EP, and I also got the other EP, MGH. So that's what the other height's for. I forgot about that. 9.81 times 1.4, because it's 1.4 above the ground. This is height 1. Okay, so at this height, it's 98.8848. Here, I forgot, I just erased that number. I don't know why I did that. It's 123.48 joules there. Okay, let's double check some numbers here. Times. Okay, then my EM, which is the sum of all the energy, not just EK and EP, because at this point, at this point, V is equal to 0, so there's no EK. So I'm going to add on the 123.4, and this is going to be 222.3648. Sorry about that. And then I've got to take that 222 number. Let me just erase all these other numbers here. Let's erase that one, and that one. There we go. So I got to take this 222 number, which is my initial mechanical energy. It's the same as my final. And then I can use that in all of these spots. I'm going to minus over the 50.65 there. Then I get 171.7398 joules. And then I'm going to use, that's a 3, that's supposed to be a 3. Okay, and then I'm going to use that. I'm going to divide by 7.2 and then 9.81. There we go. So we got 2.43. That's better. You actually get an answer. Cool. Oh, geez, not joules. Okay, so I might have to stop this here. It's getting 5 o'clock. I probably should. Yeah, I'm going to stop it here. So I'm at question 59. I was planning to get all these questions done. Can I just get this one more page done? Let's get this one more page done. Then I'll go. Okay. So we got a mass here. Yeah. So we got a mass at rest. So VI is equal to 0 on a frictionless surface. Mass P is connected to it. Mass P is connected to mass Q. So I'm just going to write some of these numbers down. 4.8 kilograms. This is 3.20 kilograms. So it's definitely going to move downwards. Unlike polio. When released, they accelerate until mass 2 hits the floor. Right now, this is 1.2 meters above the ground. What's the average power output of this? Okay, so what I'm going to have to do is I'm going to have to find out what is the change of energy here, right? Divided by time. Here's a big question. So I got to find the time it takes to hit the ground. Then I got to find the change of the energy of the system. So Q is going to lose potential, but everyone's going to gain kinetic. Okay, so yeah, so this is going to be an interesting question. Okay, so I can find out what the initial EM, so remember, to find this out, to find power, I'm going to put it over here. Power is equal to work divided by time, which is equal to the change of energy divided by time. We could just say that the change of mechanical energy. So my initial mechanical energy is going to be, there's no EKs, so all the EKs like of P of Q, the EP of P doesn't change. So I'm not too concerned about that one. But I am concerned about the one that's going to change here. So if you want to put in the P one, we can. But then when I minus it from later, because I'm going to go EM minus EM, if EP doesn't change for P, then it's not really too important. So this is 0. That's 0. And this NA, not applicable. So you don't need to worry about that. We can call it 0 if we want to. So all I have for EM at the very beginning is the energy that Q has. So my mechanical energy here is just going to be mgh of just Q. All right, so this is the mass of Q. Okay, so I'll get times all together, 4.8 times 9.81 times 1.2. So the amount of energy I have in the beginning of the system is 56.5. Okay. Cool. 2 joules. Now, we're a frictionless system. That's my mechanical energy. My mechanical energy is just going to, I don't know. We'll see how this question turns out. I'm just kind of making it up as I go, because this is usually how I approach these questions, and then see if it makes sense. So at the end, my final energy so my final energy is going to be whatever the EK of Q is when it hits the ground, plus the EK of P when it hits the ground, plus the EP of P, plus the EP of Q, right? When it hits the ground. So we have a bunch of zeros again. So the EQ of the ground, because we're on the ground, is going to be 0. And this, again, is just NA, because I'm just going to minus it out. I just have to find out what these EKs are. So how do I find the EKs? Well, I got to find the speed. How do I find the speed? Well, I got to find the acceleration. Then I got to use the acceleration with the VI is equal to 0, blah, blah, blah. Figure this out. So what's the acceleration? Well, to find the acceleration, I got to do my F net formula. This is a big question. Okay, divide by my mass. What's F net? Well, if I do a whole calculation here, I could draw a little free body diagram. We have gravity pulling this down. We have some other forces, like we have tension holding this up. We have the tension pulling this forward. We have no friction. We have gravity. We've got normal on this one here. So remember, when we do these kind of calculations, our F net is going to be the sum of all these forces in this bubble. My F net is going to be, we just start crossing these off, just this FG. Okay? So my F net is just the FG on Q. Just the one on Q there. Divided by the mass of everything. So I got to add all those masses together. So this is going to be 3.2 times, because my bubble is on everything, so it's got to include everything. So 8 kilograms. But the force of gravity, that's just on Q. So this is going to be mass times acceleration, 47.088 newtons, divided by 8. So my acceleration is 5.880 meters per second squared. Okay, so my goal here is to find the final speed, right? Because I need to use that in those 1/2 mv squared formulas up here. So this has got to be 1/2 mvf squared, 1/2 mvf squared as well. The two speeds are going to be the same because they're attached by a rope. So VI is equal to 0. What's my VF? Question mark. The D, 1.2 meters. I'm pretty sure there's an easy way to do this question. I don't know. I'm just having fun. Okay. Oh yeah, there would have been an easy way to do this question up there. What do you mean? Final, the initial, it's an isolated system. Is it isolated? It doesn't say. It says it's a frictionless situation. Well, the change of energy would be 0 then. What's the output? What would you care? What would you care for the output? Would you just worry about the change in kinetic then? Maybe that's what you want. You just want the change in kinetic. So wouldn't that just be? Oh, you have to find time. That's the whole point of this. Well, I'm trying to find time, right? I'm not trying to find the final velocity. I don't care about that. Do I? Yeah, I don't care about that. I'm just worried about the final velocity. So I'm not worried about the final velocity. I'm worried about time. So I'm going to try to find time because I need time over here. So what's my time? That's what we're looking for. That's why we're doing all this. Find time. Okay. So what formula use that to find time? So that's going to be d is equal to VIT plus 1/2 AT squared. These are hard questions. That's 0. So d is equal to 1/2 AT squared times by 2. Divide by a. Take that square root. So times by 2 times 1.2. Divide by a. Take the square root. So the time here is 0.638 seconds. Okay. Now, I'm not worried about the change in mechanical because the change in mechanical is going to be 0. I'm not going to do that. Right? What's the point of that? So what's happened here is what I actually want to do, because the output in this case is the useful energy, which is the kinetic energy. So I'm going to kind of erase some things here. Good. Okay. It's also slowing down quite a bit here. Okay. So I'm not worried about that. I'm worried about what's the change in the kinetic energy, because that's the output. That's what's useful. I've lost all my potential. I've gained all this kinetic. It started off at 0. So all this kinetic energy is my useful output energy. So what's the kinetic energy? So if I started off with 0 kinetic, and now my final has 0 potential, so my change in my kinetic is this 56 number, right? And I'm going to divide it by this 0.63855 number. And I hope I get the right answer. Oh, I got 88.5, so there's something. So we got 88.5 watts. So the mechanical change is 0, all right? But I'm worried about my kinetic. So if I look at how this works out, so EM, the change of EM is 0, which means that my change in my potential plus my change in my kinetic has to end up being 0, 0. That's like the work energy theorem. This is that final minus initial ends up being 0 thing. If my change in my potential if I move this over, if it decreases by 56, so that's what's happened, my potential is decreased by 56, then my kinetic has increased by that same amount. Okay. Yeah, I'm going to stop it there because this is a hard few questions we've done here today. All right. I'll see you in the next video. Bye.